All right, we're going to continue, but again, I think it would be helpful for me to spend the time on some of these problems that are a little bit more difficult. And so I'll just give you the main results, and then if we use them as we go through some of the problems, then we'll use them. You've got the addition rule, and they call it the probability of the union of two events. And basically what this says is that if you wanted to calculate the probability of two sets like this, A and B, if you wanted to calculate the probability of the union, well, the union is everything in A or B or both. So inside these two circles is what you're after. So they're saying that if you wanted to calculate that, calculate the probability of A, which is all of A, including that part that overlaps with B, and you're going to add that to the probability of B. So I'm going to then shade all of B, which includes the part that overlaps with A. But if I add the green region here and the blue region, you can see that this middle region I've added twice. So to balance that off, we're going to subtract the probability of the intersection one time. And this formula is related to this picture. So if we use it, then great. Odds, here's a definition of odds for E. And so here's the formula. Our book is going to write it as a fraction. Other books will write it as a ratio. Like if the odds are 1/2, they would write it 1:2, 1 to 2. So if you want the odds for E, you just figure out the number of ways that E can occur, and then the number of ways that E complement can occur. And E complement together, if you take the union of those two, they are disjoint, you're going to get the entire universal set. So another way that you'll see this is the number of ways E can occur divided by the number of ways that E complement can occur. Odds is a concept that's very closely related to probability, but it's slightly different. The probability of E, from a formula that we've looked at before, is the number of ways that E can occur divided by the number in the sample space. So you can see that they differ on the bottom number. For odds, the bottom number is the number of ways E complement can occur. And for a probability, it's the number of possible outcomes in the sample space. So I might come back to this. Here's the union of the two events, and here's the intersection. So you're going to see a lot of problems today that involve this. If we have some empirical probabilities, I'll come back to this. All right, let's start off with some of the problems, and you're going to be seeing some Venn diagrams. So the first thing that you have to be able to do is to interpret this Venn diagram. So let's talk about the number of elements in A. How many elements are in A? Let's get some interactivity going here. Why don't you put your answer in the chat? Number in A from this diagram. Okay, I'll ask these in order. Number in B, number in A union B, number in A intersect B. So just to get some, see if we're interpreting. These numbers that are in these regions here are clearly not probabilities. Number in the universal set. It's another one that you have to pick out here. Maybe we'll do the number in A complement and the number in B complement. Okay, all right, so I'm looking at the answers that you're posting. I agree that if your number in A is not just those 12, because those 38 are also in A. So you add the 12 and the 38 together to get 50. The next answer, number in B, that's right, you would add the 38 and the 23, get 61. Okay, now let's do the union. And remember, the union would be these three regions, because you want to include everything in A and everything in B. And of course, that would include, you don't want to doubly count the 38 in the middle there. But other than that, you're just going to add those three numbers. Okay, good, 73. And the reason we write these down is because we actually use these numbers to calculate probabilities. And the bottom number in a probability is always the number in the sample space. In the intersection, next one, the intersection is the area that's common to both. A intersect B. Okay, good, good. 38 in the middle. Okay, now the number in the universal set. And we have the Venn diagram consists of, I'm calling it the universal set, but I see here they called it the sample space. So maybe we'll switch this to sample space. How many are in the sample space? Yeah, so that would consist of these three regions inside the circle and then the region outside the circle as well. So you have to add those numbers plus the 27. And yes, you get 100. Good. All right, now let's do A complement. Now the way we interpret A complement is all of those that are not in A. So here's A that consists of those guys. We're interested in how many are not those. How many in the entire sample space are not those? So yeah, here's A. If we cover up those, we've got not A. And so you'd want to add the 23 and the 27. So you are correct, 50. And what about B complement? Not B. Okay, good. So cover up all of B and then go outside that. There's just 4 numbers here. So you have 4 numbers inside B. So there'll have to be two numbers outside B that you'll add together. All right, now this basically is something that you should do for a Venn diagram. And then if you do that, we're just going to use our definition. So what we have here is the number of elements in A union B divided by the number in the sample space. That's how we define the probability. So we've identified the number in the union as a top number, that's 73, out of the entire sample space, and there are 100 in the sample space. So you can write it as a decimal or you can write it as a fraction. Okay, why don't you try the next one? It's probably easier to say, just go through the 4 regions and ask yourself if, which regions are we talking about here? And remember, it's a probability. So what's tricky about this last unit is that some of the times we're just counting, like in chapter 7, and our answers are whole numbers. And then we switch immediately over to the probability section where all the answers are between 0 and 1. Fractions or decimals between 0 and 1. All right, so we want to take A and intersect that with B complement. Now, one way that you could figure out what regions you're talking about is to just go ahead and do a Venn diagram and shade the region. Now, this symbol here is intersection, so we're going to shade A, and then we're going to shade B complement, and then this operation is intersection. So what we're going to do then is we're going to look at the doubly shaded regions. So it would look something like this. I'm going to shade A, all of A. I'm going to shade B complement, which is everything outside B, right? So it'd be all that region. And since the operation is intersection, I'm going to be identifying the doubly shaded region. So you see the doubly shaded region here? That's the slice that you want to include in our probability here. So we have all of A, and then B complement would be outside of B. So then we would get rid of the 38. So we have the number in A intersect B complement divided by the number in the sample space. So that bottom number throughout is going to be, any probability that you construct in this context here is going to be the denominator is going to be 100. All right, so just those 12. You're correct, Joe. All right, now this one here, notice that the A intersect B, we know how to identify that region, but then on the outside of parentheses, you have that apostrophe. So the apostrophe means complement, the apostrophe means not those. And so what you do is you identify the number in A intersect B, and then you say, not those, but everything else. So we don't want those 38, but we want everything outside that 38. So we know that there's 100, and if we don't have 38 of them, I guess we're left with 62. Okay, so there's no permutations and combinations in these. It's just a matter of drawing a Venn diagram and labeling some of the regions and knowing the probability definition. All right, but you can see that complement is kind of sprinkled in there. All right, now if you can do this problem with Venn diagrams, then when you see something like this, you can try to convert it to a Venn diagram in this way. All right, so the 2 events we have here are D. D is the event in a 52 card deck that a diamond, D for diamond, D diamond. The number of diamonds is 13. So count the number of diamonds. F is our next event. And that's the getting of a face card, selecting of a face card. The number of face cards we have are 12. So what's the probability of getting a face card? So defining some events and then using those events defined to be specific letters. All right, so that one's fairly easy. First one, 14, probably 15, not too bad. But once you get down to these other ones, then it might be tricky. So if you do a Venn diagram like this, you know that the number in the sample space has to be 52. So when you add these 1, 2, 3, 4 regions, they have to add up to 52 because that's how many cards you have. Let's start in the middle. How many cards out of 52 are both face cards and diamonds? Because it's in the intersection, so it has to be both. Okay, good. 3. You've got the king of diamonds, the queen of diamonds, and the jack of diamonds. Those are the only 3. All right, now this region out here are also face cards, but they're outside the diamond circle. So how many face cards do we have that are not diamonds? That would go here. Yeah, the 3 face cards that are clubs or spades or hearts. So you can see there are 12 face cards when you add both the 3 and the 9. 9 of those are non-diamonds, 3 of those are diamonds. Okay, now let's focus on the diamonds. If there are 13 diamonds in the deck, there are 3 of face cards. How many non-diamond face cards are there? Good, 10. Now we've accounted for 10, 13, 22 cards, and we know that there's 52 cards in the deck, so how many must go out here? These would be the cards that are neither diamonds nor face cards, 30. And when those 3 numbers are added, then you have, all right, so I just want to give you another tool that you can use to potentially do these problems. And you can see that complements are throughout, and that's why they're in this section. You can also see that the union is in there as well. Sometimes I don't think using the formula is that useful, but sometimes it can be. And it's just another tool that you have to do this problem. So for example, I mean, what I'm talking about is this rule right here. So if you wanted to, number 20 says D complement union F. So what this formula says is that if you wanted to calculate this, what you could do is take the probability of D complement and add that to the probability of F, and then subtract out the probability of D complement intersect F. Now, if it would be easy to find these numbers, in some problems they might even be given to you, then by all means use the formula. I don't think the formula is going to be that useful for this one. Okay, 14, 16. Well, look, we're calculating the probability of D complement there, and then we're calculating the probability of, so we're actually calculating in the first 3. I didn't recognize this, but notice in part 14, we're doing this one. In part 16, we're doing this one. And then in part 18, we're doing this one. So if you use the answers from 14 and 16 and 18, you can put them together here to get the answer to 20. All right. I didn't think that there would be a connection there, but I guess there is. All right. We might not use the formula for all of these. We might not use the Venn diagram for all of these. Let's see how far we can get. Usually with these problems, there's more than one way. So we do know that the number in the sample space is 52 because there's 52 card deck. So for all of these, the denominator is going to be 52. The probability that we would select a face card, 12 out of 52. The probability that we would select a non-diamond, you can see there are 39 non-diamonds. The probability that we would have a non-diamond and a face card at the same time. Which number are we talking about here? Can't be a diamond, can't be a face card. 30 are left. Okay. And just remember the regions. I think we did this in an earlier section. This is F intersect D complement. It's in F, it's outside D. This one is F intersect D, inside F and inside D. This one here is outside F and inside D. And this one here is outside F and outside D. So if you can link these numbers, all of them are intersections. You've got the 4 numbers. So this would be non-diamonds that are face cards. There are 30. Can't be diamonds, can't be face cards. Hold on. This one says, I think I was doing this one. Non-diamonds and non-face cards. This one would be non-diamonds but face cards. So it's the 9. Okay, now union. Now, union means we're going to put all these together. So we're going to put all the non-diamonds together, 39 of them. We're going to put those together with the face card. There are 12 of them. 39 and 12 is 51. However, we don't want to count those 3 diamond face cards twice. So we're going to have outside of D, so then we're including those 2. No, let's see, union. So we're taking these 39 and we're going to put it together with F. So we're going to add those 3. So what is that, 42? 42 out of 52. And of course you can reduce these fractions. And, oh, this one was the 30 out of 52. This one's going to be a little bit higher because you're going to union everything outside of F with everything outside of D. So the only cards that you're not counting are these 3. So that means you will count 49 of those cards. So what this would mean in words is, what's the probability of when you randomly select a card that it is either a non-diamond, that means it's a club, heart, or spade, that's one of those suits, or it's a low card, a non-face card, one or the other. And this covers all the cards except for the 3 face card diamonds. Okay, so here are a couple of problems using Venn diagrams, and you actually have the numbers inside the Venn diagrams. You just as easily could put probabilities in each one of these. Since this one's easy because the number in the sample space is 100. So if you take 12 and divide by 100, you get 0.12. If you take 38 divided by 100, you get 0.38, 0.23, and 0.27. So now when you're asked probabilities, all these numbers in these regions are probabilities. You don't have to worry about dividing them by 100, and you can answer the same problems. Okay, I'll do all of the problems on this worksheet here, but I have to pick and choose in terms of the ones that I want to do with you today. For this problem here, it's a lottery game where a single ball is selected. So in a situation like this, what you might want to do is just to list out all of the different balls with the different numbers on them. It's easier when they're listed out this way to count them all. So you're selecting one ball from 25, and so if you want to know what's the probability of selecting a 6, then there's just one ball that has a 6 on it, and there's 25 total, so it'd be 1 out of 25. But you'll notice here that all of these say or. And so what they really want you to see is the probability of A or B, which is the probability of A union B. So all of these problems involve, the addition rule for a union. But I think you can do these by just looking at these numbers. So let me just do one of them, like number 30. A multiple of 3. All right, so I'm going to go and select all the multiples of 3. 3, 6, 9, 12, 15, 18, 21, 24. Those are the multiples of 3, or the multiples of 4. So I'm going to select the multiples of 4. 4, 8, 12 has already been selected. 16, 20, 24 has already been selected. So when I add up all the numbers I selected, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12 out of the 25 balls. So you can write the simplified fraction version, or you can write the decimal version. Number 34 deals with complement, and the way this works, if the probability is 0.03 that an automobile tire fails in less than 50,000 miles, well, if it doesn't fail, it either fails or it doesn't fail. I mean, there's no in between here. So if we wanted to calculate the probability that it did not fail, we could use the complement rule. So the probability of E complement is equal to 1 minus the probability of E, where E is that the tire fails. And if the tire does not fail, or if it's the opposite of failing, then it does not fail. So this is one use of the complement rule. You know that the probability that the tire fails is 0.03, so the complement of that is 1 minus. And then we would interpret this probability to say that, if you buy a 50,000 mile tire, there's a 97% chance that it will still be working after 50,000 miles. Let's get into some odds problems. So what I'm going to be using primarily is this worksheet that I showed you here. You can do the odds for or the odds against. So pay attention to what they're asking for, odds for, odds against. And the only difference is that you can compare these two. You just switch the numerator and denominator. The odds for E would be the probability of E over the probability of E complement, and the odds against E would just flip those two, the probability of E complement over the probability of E. So this is what we're going to use. More specifically, I might use this version of it, the number in E divided by the number in E complement. All right, here's how some of these problems will come out. It says, given the problem, the following probability. So the probability of, here's one way you can do it. The probability of, well, let me just do it this way. The odds for E is equal to, I'm going to use the fact that they tell us that the probability for an event E is 3/5. So the probability of event E is 3 over 5. And we know that the odds for E is the number of ways that E can occur divided by the number of ways that E complement can occur. So if we can figure out the number of ways that E can occur, maybe we want to do the probability here, we can calculate the probability of E complement if we know the probability of E because of this formula up here. We can calculate the probability of E complement just by taking 1 minus the probability of E, which is 2/5. Now, the odds for E is given to be one of these two, the probability of E divided by the probability of E complement, or the number of ways E can occur divided by the number of ways that E complement can occur. The one that probably makes sense here, since we have both of these, we can use the number or the probability of E divided by the probability of E complement. So there's our definition of odds. And we just calculated, we were given that the probability of E was 3/5, and then we divide by the probability of E complement that we just calculated to be 3/5 or 2/5. So if you multiply the top and bottom by 5, or however you want to do this, and simplify, the 5s will cancel and you'll get 3 over 2. And the first thing that you'll notice here is that in some cases, the odds will be a number larger than 1. That's possible. If you do enough of these, you'll go right to the answer. Okay, so what about B? Why don't you try B? Give me the answer to B. Okay, 1/6. In the next problem, we're doing the opposite of that. We're kind of starting with the odds in favor. And I guess I would recommend, if you're going to do this one, so what they're saying is that the odds for E equals 5/9. But we also know that the odds for E is equal to the number of ways E can occur divided by the number of ways E complement can occur. So if we just say that the number in E is equal to 5 and the number in E complement is equal to 9, then we have the number in the sample space is equal to 14, which is 5 plus 9. It's always going to be the case, since E and E complement are will basically take into consideration all the possible outcomes. You're either in E or you're not. So if we add the number in E with the number not in E, we're going to get the number in the entire sample space. So if we want the probability of E, then we take the number of ways that E can occur and divide by the number in the sample space. So number in E is 5, number in the sample space is 14. So we're working backwards, but the answer to 42A would be 5/14. And if you kind of see the pattern, I'm not going to give it to you. I can give it to you, but it's not going to make any sense. If you see this pattern, you'll be able to do these pretty quickly, because basically we add these two numbers. We take the top number, 4, and then we put it over the sum of these two numbers, 7.